Good morning everyone. Myself Vishant from Mechanical Engineering Department of Ganga Institute of Technology and Management. Today I am going to discuss this very important topic of refrigeration and air conditioning, which is vapor compression refrigeration system. Refrigeration system, as you know, that it is a process in which we remove the heat from any space to keep it at a lower temperature as compared to the surroundings. And for doing this refrigeration, we are using a special arrangement which is called vapor compression. Vapor compression, as the name indicates, in this we are compressing the vapors to perform our desired operation. Okay. In this type of refrigeration system, we have the four main elements which are shown here in this diagram. These four elements are evaporator, then we have compressor, then we have a condenser and expansion valve. These four components work together to give us the refrigerating effect in a controlled space. Okay, we are going to understand this whole process using this diagram in which we have shown all the four components and their relative arrangements. First of all, we need to understand the working of all these four components. Let us talk about the compressor. Compressor, as we know, that compressor is used to increase the pressure of vapors. So, in the compressor, the refrigerant will enter in the vaporized state. Its pressure and temperature will increase when it passes through the compressor, and it will flow in this direction. After the compressor, we will have a heat exchanger, which is called as the condenser. The purpose of this condenser is to liquefy the vapors coming from the compressor. As we have seen that the compressor is discarding the vapors at high pressure, this condenser will operate at the same pressure. As we all know that all the heat exchangers are basically the constant pressure devices. So there will not be any change in the pressure, only the state of the vapors will change to liquid. At the end of the condenser, we will have a high pressure and high temperature liquid. This high temperature, high pressure liquid will then flow to an expansion valve. The purpose of this expansion valve is to reduce the pressure of vapors. The refrigerant will be brought back to a lower pressure where it will be used in the refrigeration system. So expansion valve, while passing through this expansion valve, the pressure and temperature both will decrease for the refrigerant. As the pressure and temperature decreases, the vaporized state of our refrigerant will change to liquid plus vapor. Okay? So the next component is our evaporator. At the inlet of our evaporator, we have a liquid plus vapor mixture. This liquid plus vapor mixture will pass through this heat exchanger, which is called as evaporator. While passing through this evaporator, this refrigerant will gain heat from the refrigerated space. So as it gains the heat, the liquid portion of this refrigerant will vaporize, and we will get a low pressure vapor exit at this point. So then again this low pressure vapor will enter the compressor and the whole process will continue. So this is the main basic working of the four components which work in a cycle to give us continuous refrigerated effect. Okay. Now we will see the thermodynamic aspect of these processes. As we have seen that these are the four components that are working in cycle: evaporator, compressor, condenser, and then expansion valve. Now look at the thermodynamic process that is taking place in these components. First of all, we talk about this. When we are talking about this compressor, the process inside the compressor is ideally isentropic process. So in isentropic process, the pressure and temperature will rise. Then condenser will work at the constant pressure process, and then expansion valve will result in the lowering of the pressure. During the expansion valve, the process called as the throttling will take place, and during throttling the enthalpy of the refrigerant will remain constant. That means the total energy in the refrigerant will remain constant, and then this refrigerant will pass through the evaporator, where it will gain the heat from the cold refrigerator space. It is going to gain, and it will change its phase from liquid plus vapor to vapor state. Okay, so now we are going to represent all these processes in our TS diagram. TS diagram it has a temperature represented on the y-axis and entropy on the x-axis. So the process 1 to 2 is representing our compressor, in which the process is isentropic. It consumes some work, which is represented by W. Then the process 2 to 3 is a constant process, which is which results in the rejection of heat from the refrigerant to the warming. Then from point 3 to 4 we have isenthalpic process inside the expansion valve. Isenthalpic process is represented here. The inlet of the expansion valve is having the saturated liquid, and then exit of the expansion valve will be inside these two saturated liquid and saturated vapor lines. It means it is a mixture of liquid and vapor. Then next and the most important step is the passage of the refrigerant through this evaporator, where refrigerated effect is being generated. So point 4 to point 1 is the process in the evaporator, which is taking place at the constant pressure, and it is gaining heat. Refrigerant is gaining heat from the refrigerated space. Okay. This is another representation of our VCRS cycle in the pH and PV diagrams. This is pH diagram, in which we have represented pressure on y-axis and enthalpy on the horizontal axis. So we can see that the compressor here is represented by this line, dotted line, which is representing that the energy of the refrigerant is continuously increasing. Pressure and temperature both are increasing. As a result, the enthalpy is also increasing from point 1 to point 2. Then from point 2 to point 3 we have constant pressure process inside the condenser, which is represented by a horizontal line. Then from point 3 to point 4 we have isenthalpic process and throttling, which is represented by a vertical line, as the enthalpy is on the x-axis. Then point 4 to point 1 will be again constant pressure process inside the evaporator. So this is represented in this way. Next we try to find out the important parameter by which we can measure the performance of our refrigerating system. This is usually measured with the coefficient of performance. Coefficient of performance basically represents the ratio of the refrigerating effect that is generated inside the refrigerator to the work input that it is taking. So in our cycle we have already seen that refrigerating effect is taking place in the evaporator. This process is representing our refrigerating effect 4 to 1, and work input is given inside the compressor. Okay, so the work input will be given by H2 minus H1, whereas the refrigerating effect will be equal to H1 minus H4. So we are calculating their ratio to find out the coefficient of performance. Q in divided by work consumed will be equal to H1 minus 4, H4 divided by H2 minus H1. This is the coefficient of performance. Next is a reverse Carnot cycle. As we see in the vapor compression refrigeration system, it is also important to compare our cycle with a ideal cycle of any refrigerating system, which is our reverse Carnot cycle. Just like the Carnot cycle, which gives the maximum efficiency in case of power generating cycle, reverse Carnot cycle has the maximum COP for all the refrigerating systems. So it sets a standard from which we can measure the performance of our VCRS cycle. So usually the Carnot coefficient of performance is given by this formula, in which we are taking the two temperatures, which is cold body temperature and hot body temperature. Tc by Th minus Tc will give us the coefficient of performance of our reverse Carnot cycle. Next. These are the normal processes that are taking place inside our reverse Carnot cycle. Main changes in this cycle as compared to the VCRS cycle are that here the evaporator, basically the expansion valve is replaced by turbine. Okay, the evaporator is there and compressor, condenser. Three components are there, but expansion valve has been replaced by turbine. But the main main reason because this cycle is having maximum efficiency is the processes that are taking place inside this. First of all, 1 to 2 is the isothermal heat transfer process. 1 to 2 in evaporator, earlier we have seen that the process in the evaporator was constant pressure, but now we are having isothermal heat transfer process. Then in compressor we are having isentropic compression, and then in condenser we are again having isothermal heat rejection, and in turbine we are having isentropic expansion. So we are we can see the TS diagram of this complete circuit. Next. Here are some of the limitations why reverse Carnot cycle is not generally practical to use in industry. These are the two main reasons why we are not using reverse Carnot cycle. First is that the isentropic and isothermal processes are basically ideal processes. Okay, so working these two and that two continuously one after one is very impractical task. In isentropic process, the pressure increases quickly, whereas in isothermal process the pressure has to change very slowly. So maintaining these two processes one after one is a very tedious task. Then another reason why it is not used is that addition and rejection of heat at the constant temperature is impossible. As we have seen that the heat transfer processes in the evaporator and condenser are both the isothermal processes. Isothermal basically means that the temperature will remain constant. With temperature remaining constant, and it is very much impractical to add heat into the system. So these are the two drawbacks which is the reason why we are not using reverse Carnot cycle. Okay. Okay, that's it for today's class. We will discuss this topic further in the next lectures. Thank you so much.